Okay, good morning. We're going to take a look at all of the ancillary equipment and the boiler. And we're going to basically be following through the P&ID drawing that you guys have got in front of you. So you should have that and refer to it as we're working our way through. We're going to start off with the water side from the deaerator and the hot well, and then work our way through to the feed water getting into the boiler, take a look at the boiler drum, and then from there we'll look at the blowdown, continuous blowdown system, the water level controls, that kind of thing. And then we'll break it and we'll go into a separate system where we start to look at the airflow and the fuel flow. And we're going to logically work our way through the system completely to go through the complete P&ID. Okay, so I'm up on the mezzanine floor right now where the hot well is and the deaerator. So Charles, if you go around, you see we've got an identification tag sitting on the hot well itself. The hot well has got freshwater makeup air, so we go up over to here, water I should say. This is domestic cold water, non-potable cold water that comes in as makeup water. Most of the water that's coming back here is actually coming back as condensate. And so there's another line coming up from the floor down there. No, that's the overflow, sorry, not this part. The condensate header is right here, over my head. All the condensate comes back from SW1 building, from the instrumentation process lab that you guys worked in last year, the thermal lab, and also from the 103 header. That condensate comes down and comes into the vessel at the bottom. Inside there's a tube which has got holes through it, and what it is, it's a sparger tube, just like the spargers that you saw back on the evaporators, and it's allowing the hot condensate, which is going to flash into steam, to get back in here, because the condensate is coming back at probably about 105, 108 degrees C, and once it gets into this vessel, which is vented, it's going to flash into steam, or some of it will. Over here, on the top of the deaerator, or the hot well, I'm sorry, is this line here, which is a vent. This is going up through the roof. So this vessel is running at atmospheric pressure. From the hot well, in a few moments, we'll go downstairs and see the pumps. And then from the pumps, it pumps the condensate from the hot well up on this line here, which goes over and comes into the deaerator. In the deaerator, we control the water level down below the half level. This line right here is an overflow line, so the water level will never go any higher than that. Anything that does overflow from here goes down to a trap. I don't know how easily you can see it. The trap is right there, the great big thing, and that trap opens up for water or condensate, and that goes down to the blowdown separator in the basement. So this is the maximum level it can get to, because the spray nozzle, which you'll see on another video, is down to about here, and yet are bringing the water in and it's spraying and separating, and that helps the deaeration process. And so the deaerated water sits in the bottom. The air that was in the condensate that came back, or the fresh water that comes in, will actually collect in the top, and there's a vent line right there, and there's a valve that we've got to open a little bit later, and that vents out to the roof. So in a running steam plant, you would see a small vapor stream coming up from the roof all the time, and you might think that's wasteful, but in fact that is the deaerated water, or the vapor that's coming out the top, getting rid of nitrogen, oxygen, and all kinds of other gases that we don't want in our water. The water down in the vessel will be somewhere in the order of 5 to 7 parts per billion as dissolved oxygen. We need to get that oxygen level down very low. So we've got basically level transmitters on here. That's what this guy is. We've got here a pressure transmitter, because we're going to control the pressure by putting in fresh steam. And then the deaerated water will come out through that valve there and go down to the feed water header. And then the feed water pumps will pump it from there. So now we're going to go downstairs and take a look at the pumps. So before we go downstairs to look at the feed water pump, one remaining thing that I just thought of, we've got a freshwater makeup valve right here. That automatic control valve is part of the split range circuit that actually looks after this. So if they can't get enough water out of the hot well, then that valve opens up at about 40% output signal and starts to add fresh water makeup. So we've got a block valve that's there that we would have to open before startup, and then from there it gets added into the condensate stream. The condensate from the hot well is coming this way. Any fresh water makeup we need comes that way. They go and join together and they go down into the aerator vessel and go through the spray nozzle. Okay? Okay, so now we're down here at the feed water pumps. A little bit noisy in the background. The condensate coming out of the hot well comes up from upstairs on that header right there, and it either comes down into condensate pump number 1, this way, comes down into condensate pump number 1 and out, or it can come out at the end of that line down that way, condensate pump number 2, and then come into this header. This discharge header is going to end up going upstairs and over into the deaerator, where it is deaerated. And a few moments ago we looked to see where that condensate was coming in. So coming out of the deaerator, you can't see this very well, but up in there is the valve, and it comes onto this header. So this is the supply header for the feed water pumps. Number 3 feed water pump, this is its inlet valve, the strainer on it, outlet valve, going up to the boiler feed water header. So up here, labeled as boiler feed water, it's going to the boiler. That's pump number 3, which is a fixed speed pump. The pump that discharges the header. If the pressure is over set point, there's a control valve up there that will let down the pressure back into the deaerator, back to the supply of the feed water pump. And so that's how we control the pressure. The pump can probably generate 2,800 to 3,000 kilopascals. We're controlling it down at 2,400 kPa by bleeding back. We've used that type of control for the pump blending system that people have worked with previously and with other controls. So there's nothing unique about it. It's fairly common. It's got a very special valve up there because of the high pressure drop across it. It's called a link and lock valve, and they're made by Mason Nealon. Now, the feed water pump number 2, which is this guy here, draws its water off that same header, and it's running on feed water pump number 2, goes through the strainer, into the pump. These are 11-stage pumps. They're multiple stage pumps to get up to the high pressure. Then discharge back out of there, and again back into the boiler feed water header. This pump, we control the speed of the pump with a variable frequency drive, which is located over here. So the output from the DCS actually sends up 4 to 20 sends a signal to this guy, so we're actually controlling. It's not 4 to 20, it's actually coming out as a digital signal running on control net. Okay, and the third pump is actually a steam turbine. So the turbine is in this part underneath the blanket here. Steam line comes in here. Right over my head, there is a steam control valve right there that is controlling the amount of steam that we put in. The governor on this pump, and we again are controlling the speed of the pump. The feed water is being drawn in from the suction side, which is this line here, through a strainer, into the pump, out of the pump. Okay, the line goes up to there and joins right about here with that feed water header. Boiler feed water came from pump number 3, from pump number 2, or from pump number 1, and then goes upstairs and goes into the deaerator if you're doing letdown control. Okay, we're back upstairs because the feed water line came up. This is the feed water line right here. the feed water comes up on this line. If I could just back up a little bit, right there is a T. Through that line, it comes down and goes through this Mason, Neal, and Lincoln lock valve, and that valve is controlling the pressure. Okay. In fact, the pressure is being sensed right here. There's the pressure transmitter, and I don't know whether you can see it. Right now, it's running at 2,070 kilopascal, which is typically what we're trying to run at. Now, the feed water comes off this header, and it goes to the boiler. So, following from there, we go through, and this is an orifice assembly, an integral orifice assembly. The upstream diameters go at that flange to the orifice. So from this flange, all the way down, goes to the orifice, like which is right there. And then from there, down to that flange is the downstream diameter. So the upstream and downstream diameters are fixed. From there, differential pressure is sensed by this flow transmitter. So this flow transmitter right now should be showing no flow because we're not running the boiler. And this is actually a smart transmitter. It's a multi-variable transmitter which actually looks at the differential, and then it knows what type of orifice plate you got in there and exactly what the flow should be. And this is actually running 4 to 20 milliamps signal. Our airflow transmitters are the same. They're smart multi-variable transmitters. Okay, we're going to go to the boiler next, so we got to go back down and cross up to the boiler. Okay, so that big black square thing that's sitting up there, rectangular thing, is the economizer. And we've got to go follow the feed water line. If you follow my laser, I'm on the feed water line right there. So it came from upstairs and it's going to go to the boiler, but before it gets to the boiler, it's going through the economizer. To get there, we're going to have to go up a ladder and onto that deck. Okay? You want me to carry that up? You want me to go up? Okay, we're up on the deck. Behind me here, or just in front of me, is the economizer itself. The feed water is coming in on this line up here and drops down like so. Goes down, and down below us is the feed water valve. And that's important. The feed water valve is on the upstream side of the economizer. If it's on the downstream side of the economizer, the feed water valve gets subjected to extremely high temperatures, and I've seen them fail. So to be installed properly, they should be on the upstream side of the economizer. Now, the water's coming out of the feed water valve here. The economizer can run in bypass, two different modes. Bypass of the liquid or bypass of the gases. If you're bypassing the liquid, you would close the inlet valve and open this bypass valve, and then from here it would come up and go straight across, and this line coming out the end of this sort of header is going to the boiler drum at the front. If, on the other hand, you want to go through the economizer, which we always do, you'll take the water through here. This valve's going to stay closed. You'll see that we've got a do not operate tag on it, so if somebody doesn't accidentally open it. We've got do not close tags on this so that they don't mess it up. The water comes into a header here, and on this header, there's tubes going all the way along the side. And those tubes are where the gases will go. So here we've got a damper. And right now it's shown in the bypass position. The flue gases are just coming straight up and out, not being directed through the heat exchangers of the economizer. If I take this economizer and put it into operate mode, what I've just done is I've taken a damper and I've moved it to that position, which now means that the gases are being forced out, up through these tubes, goes around the back, comes over the other side, comes out on these tubes, which comes out on the top side, and comes out on these tubes, and then gets forced through this bank of tubes on here, and then finally comes out of here as hot water. We typically will pick up 20 to 30 degrees C temperature rise on the water coming in and going out. And then again, locked open, do not operate. We come down, this guy's closed, so the water has to go in there, has to come out this way, and this valve is closed. And in normal operation, we will try to put this guy in service mode. For startup, we actually take and move it to bypass mode because we want to make sure that the flue gases are hot. And in one of our other videos, you'll see in operating the boiler, we talk about a temperature probe sitting up at the top of the economizer, and the temperature probe is located right here. And this is just a thermal switch, okay, build thermal system switch, and the sensor is sitting right there, measuring the amount of temperature in the flue gas. We want to get that up to 105 degrees C before we can get a release for modulation from the burner management system. So this is the switch that's got to do it. Now, what we're going to do next is we're going to go downstairs and we're going to look to see what, before we do, while we're up here, this is the steam drum. And you can see the safety valves there, and the non-return valve right there. This guy is set for 305 PSI. This guy is set for 300 PSI. And then you can see that the steam will come out on here, and then there's drip legs and condensate drain sitting on there. The drum itself is sitting in here. This is a vent or for Blowdown, which is normally closed. This line at the bottom, this is a chemical feed line. So our chemicals are actually coming into the boiler drum, and that pipe goes about halfway up the drum, and then it gets distributed. Well, actually, it goes full length of the drum. It's got holes in it, and we distribute. Okay? So our feed water is coming in on this line here from the back of the economizer, comes through and drops down on that leg there, and then there is a check valve, and then a hand valve, and then I come up on this line here and go in, and that is our feed water inlet right there. And again, at that feed water inlet, the pipe goes into the boiler, goes down to the far end, it's blanked at the end, and then it's got holes. And the holes are set such that they don't blast down into the tubes. They actually blast out, so they're just over top the tubes, so they don't interfere with the downcomers and the risers. Okay, that's very important to make sure that's done properly. While we're here, our water level transmitter, the taps are there. And you can see the tap coming off, and there is my condensing reservoir, which is nothing more than a 2-inch pipe T. And then there is the high pressure tap right down there, and that's going down to the drum level transmitter, as is the compensating leg going down to the drum level transmitter. Okay, we're going to go downstairs. Okay, we're back down on the main floor, and you can see the drum taps. That's the high pressure tap, the high level tap on the bottom of the drum, the compensating or low pressure tap on the top of the drum. Come down through settling chambers and settle the sludge out, and then off of their taps at that point and that point coming into the drum level transmitter. The high pressure tap, where my laser is pointing right now, the H, is actually connected to the bottom of the drum, and the L that's sitting on there, the low side of the transmitter, is connected to the top of the drum. And that may seem confusing, so because some people might just look at it and think, well, the H has to go to the top. No, the H has to increase relative to the L to increase the output on the transmitter. Okay? One more thing. We are now going to go and look at the blowdown, constant blowdown, which is coming out the back of the boiler. So that's the next step. So we'll go around the back. Okay? So the CBD, continuous blowdown, is coming from here. It comes from the upper floor. It comes from the bottom of the drum. the actual tap goes across the drum, and it's just below where you normally run the water. It's usually just under the 0 mark, and we run ours at +3. It's probably down at -5 centimeters, something like that. The blowdown comes to this connectivity sensor, which is the connectivity of the water that's coming out of the blowdown. From there, we go through these 2 hand valves to this control valve, and in fact, it's hard to see, but there's actually an orifice in here which limits the amount of flow. And that little tiny tab that's sticking out of the end of that union actually holds on to the little orifice plate. Okay, so that guy right there. So he's controlling the flow rate. This is just an on-off valve. The blowdown controller itself is a sample cycle type of controller. What happens is that once every 30 minutes, it opens this valve. Okay, so this valve opens, and you start to get a flow coming through that orifice, and then heading down to the blowdown down below to a condensate separator. The condensate that's going through there is measured by the conductivity cell back there, and it comes into here. Right now it's showing us that we got about 1160 microsiemens per centimeter. Typically we want to run up around 1500. That will depend upon the boiler and the application. Every plant is different. You do operator tests on the boiler water and determine when that water is really good. It's got the right amount of caustic in it, it's got the right amount of sulfite in it, it's got the right amount of phosphate in it, the right amount of amine in it. And once you've got all of those guys right, we look to see what is the conductivity. This guy can be calibrated fairly simply. It's just a 1-point calibration, and it's accurate when the boiler is hot because there's no temperature compensation or any of that kind of stuff in it. It is raw conductivity. So normally it's somewhere around 1800 microsiemens per centimeter. So what we'll do is we'll actually take a sample of the water, see what the conductivity is, and then go through a single point calibration on here. Just like you would do with a nuclear density gauge, or you would do with a refractometer, to basically zero it to the process. We do the same thing with this guy. So what he does is that if the conductivity of the sample you are now taking is over the set point, the valve stays open and basically blows the boiler down until the conductivity comes down to set point. When it comes to set point, it closes the valve. If at the end of 1 minute the conductivity is down to set point or even below set point, then what happens is the valve closes. So it's only open for 1 minute unless the conductivity is above set point. And then what it'll do is it will bring the conductivity down. If the conductivity can't come down, i.e. it's really high in there, the back behind it, right here, is a bypass valve. And this bypass valve has got calibration marks on it. And we can actually open or close that valve. So if the conductivity is too high and you can't get it down inside the 30 minutes, you open this valve up a little tiny bit. And the operator will do that. And it's a matter of just opening it up so you finally get to the point where this guy is controlling. It's almost like a gap action control system, where this is the major and this is the minor. And basically that's how it operates. So there is another blowdown, much larger blowdown, and for most boilers, depending on the condition of your feed water coming in, many plants, they could be blowing down through the bottom blow valve, this guy here, and in an earlier clip you would have seen a trough at the bottom of the mud drum where the liquid would actually come into it and then come out through this blowdown valve. And there's 2 of them on here. Now it's important the order with which these are opened, but more even so for closing them, because these valves, I'm going to get this down here on the this valve is a plunger. So, and when you open it, it really doesn't matter which one, but typically we'll open this one first and then this one second. And we'll blow down. And we watch the water level, which we have actually brought a remote indication to the back of the boiler so you can see what it is. Because typically they will blow it down and you don't want to trip the boiler. This is done while the boiler is running. So I would bring this down to maybe -3 centimeters and then close those valves off. And that pulls a fair amount of water out of there and gets rid of all the sludge that's accumulated in the mud drum. That's why it's called the mud drum. It's where the sludge will accumulate. So now back down to the valves. Open one. That's going to put water up to this plug. Open the second one. It's going to start blowing down. And then you're watching that water level coming down, 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 down. Now, the order with which you close it is critical. You close this one first. So that plunger goes down and closes that seat. And then you close this one second. If you make a mistake and you close this one first, you've got water trapped in here. When you close this one, you will overpressure it. Think about a hydraulic deadweight tester. And the pressure in here could split the body on this thing because you've got a tremendous amount of force on it. So again, closing. Close this one first so that the water that's inside it that can actually get pushed back to into the drum. And then close this one second. Okay, good. Okay, this is almost the end of the feed water. One of the things we missed, so we didn't have to run up and down stairs. The feed water came in there to the feed water valve. So that's the mezzanine floor up above us. So the feed water line came in here, came down. This is a bypass for the automatic valve. These are the block valves, which are manually closed very tight. This is our feed water valve, and then from there we come out. So this is the inlet valve, this is the discharge valve for isolating the feed water. So when we go to start up, we're going to have to start these guys up. So now we've got water going up into the economizer, out of the economizer into the drum. So that's taking us through our full water circuit. Okay.